Right, section 5.5 is where we've left off. This is going to be properties of logarithms. There are a ton of properties of logarithms that you guys need to commit to memory. Right now, my calculus class is struggling with remembering the properties of logs, and they're taking derivatives of logs. Well, the derivative part by itself is not that bad. They're just forgetting the rules for combining logs so that they can simplify things. So this part is very important if you're moving on to calculus. It says show that log base a of 1 is equal to 0. Well, right now, all we have in our toolbox of formulas and stuff is that definition of a log, which says y equals log base a of x if and only if a to the y equals x. So let's rewrite this log then as an equivalent exponential expression. So what would the base of that exponent be? A. What would the exponent be? 0. So anything raised to a power of 0 except for 0 is going to be 1, but 0 can't be the base of a log anyway. It's not in the domain for the definition. This we verify, and we kind of accept then that this is a basic truth. Last time we went over graphs of logarithmic functions, didn't we? We talked about logs being inverses of exponents and how exponential functions have intercepts right here at 0, 1. Well, logs have x-intercepts at 1, 0. When x is 1, y is 0. You can verify that graphically and also using properties of inverse functions. The x-intercept for logs is 1, 0. Any inverse function will be symmetric about the line y equals x, and logs are inverses of exponents and vice versa. So those inverse properties are good to know. That was from section 5.2. Next, we're asked to show that log base a of a equals 1, and we're going to do this basically the same way, rewriting the log as an equivalent exponent. So the base of our exponent will be a. What is the exponent? 1, and that's going to be equal to a. The argument, remember, stands alone. A to the first is equal to a, is it not? So we've just verified this as well, just simply by rewriting a log as an equivalent exponent, because this makes sense to us in the exponential form. We're more used to exponents. So we have another property of logs. These I don't really consider properties, these two. When they summarize all the properties, they're going to include them, but to me, these are things that you can figure out just by rewriting a log as an exponent. So I don't really stress memorizing these. I guess life is good if you do, but it's not necessary. These, on the other hand, I would memorize. These are called the inverse properties of logs. Remember when we did inverse functions, we said that if you composed a function with its inverse, you're going to get out whatever it is that you put in. And we also said that logs and exponents are inverses of each other. So here's an exponent base a, and inside of the exponent we have a log base a. So the argument then is what we're going to get out, because we put in an m into our logarithmic function. Essentially what happens is these two things is like square and a square root. The exponent base a and the log base a are going to cancel each other out, and what you get is whatever you put into the log. Same thing if you put an exponent inside of a log. Log base a of a raised to a power is that power. Okay, once again, the log and the exponent cancel each other out. And this comes in handy because in the world of calculus, we would like to cancel out ln's and e's. The natural log of e to the x is x. That comes in handy. We work a lot with natural logs. Ln's and e's cancel each other out because they're inverse functions. Remember, a natural log is a log base e. So let's look at these problems. Log base pi of pi to the third is 3. This is just an example. Notice the log base pi and the pi raised to a power are going to cancel each other out, and we just get what this is equal to. 5 here is the base of the exponential equation, and 5 raised to the log base 5 of the square root of 3 is the square root of 3. And like I said, ln's and e's cancel each other out, so this is going to just be equal to 0.035t. This is something that's really worth remembering. If we had log base 7 of 7 raised to the x squared plus 2, what would this be equal to? So you've got it. That's a typo. So glad you caught that. That should not be there. That 0 is a typo. Yeah, they moved the decimal point. So the product rule for logs basically says that if you have a product in your argument with a log base A, you can separate that out into the sum of two logs with the same base. When I say the words for the exponential rule, the one that we had that was like that, where we had a to the m times a to the n equals a to the m plus n. This is the product rule for exponents. And what we say is when you multiply with a common base, we add the exponent. Now listen to the words that I'm saying and remember that logs are equal to exponents because that log is equal to y, a log is an exponent. So listen to what I'm saying. When you multiply with a common base, you add the exponents. The logs are equal to the exponents. The same words apply for the, matter of fact, I should probably write those words down for people who are not here. So the log here is equal to y, and y, when we rewrite it as an exponent, is the exponent. So that's the product rule. So we're going to use this to both expand logs and contract logs as needed when we start solving equations. Then we have a quotient rule for logs. Remember the quotient rule for exponents? It says if you divide with common bases, what do you do to the exponents? Likewise, then, if you divide with a common base, you subtract the exponents. But I want to caution you, this is not the same thing as saying log base a of m divided by log base a of n. A quotient of logs is not the same thing as a log of quotients. They're two different things. This can't be simplified. It is what it is. And then we have the power rule. So that's the product rule, the quotient rule, and to that we're going to add the power rule, which says basically if you raise a power to a power, put the power inside of the log, you multiply the exponents. Well, because the log is an exponent, and r is an exponent, we're multiplying the exponents. So the rule that I want you to think about is if you raise a power to a power, you multiply the exponents. But doesn't it look like what's happening here is we're taking this exponent and we're moving it down front? That's another visual cue that hopefully will help you realize what you need to do here. So we're going to use these properties now. Hopefully you have them written down, and we're going to use them to expand the sum of the logs. And the process we're going to go through will be the same every time, and it will make your job so much easier. It'll take the quotient rule out of play, first of all. So your first step here to expanding is rewrite the argument. I want you to rewrite the argument so that there's no radicals. We're going to use rational exponents. And if we had a quotient, we'd get rid of the fraction. We'd use negative exponents. In this problem, I want you to remember that a to the m divided by n is the nth root of a to the m. So that's how we're going to rewrite this cube root as a 1/3 power. And also, 1 over a to the n is equal to a to the negative n. So we're going to use negative exponents to replace fractions, and we're going to use rational exponents to replace radicals. Your next step then will be to expand using the product rule. So we rewrite the argument with addition between all of the logs. And then finally we're going to use the power rule. So we're going to use the power rule to bring all the exponents down. So going through this process then one step at a time, our first step here is to rewrite this as log base 2 of x squared times x minus 1 raised to the 1/3 power. That's our first step. The second step is to rewrite this as log base 2 of x squared plus log base 2 of x minus 1 to the 1/3 power. See how we expanded using the product rule? And then we're going to use the power rule and bring this power down, and that's going to give us 2 times log base 2 of x plus 1/3 log base 2 of x minus 1. This one is a log base e. We're going to follow these same 3 steps up here. Hopefully you have them written down somewhere or you'll remember what to do. For our first step, what do we need to do? Rewrite this as the natural log of x to the third, x minus 2 to the 1/2, x plus 1 to the, no. I said rewrite the argument so that we get rid of the fractions and the radicals. We want the fractions and the radicals gone because now we don't have to worry about the quotient rule. We just worry about the product rule. And it makes life so much easier. So this then is going to be written into how many sums of logs? 3 of them. We have the natural log of x cubed plus the natural log of x minus 2 raised to the 1/2 plus the natural log of x plus 1 to the negative 2. And then we drop the exponents down, and this becomes, those 3 steps work every time. And guys, this is not the only way to present this information. And as a matter of fact, I used to teach it differently, but I had a student point out to me one time, look, if I do this in this order, it works all the time and it's less stress. And I'm like, yeah, because people would get bogged down on the quotient rule if we had more than one term in the denominator. I'm going to insert a problem here that I'm going to make up, and I want you guys to solve it, and I'm going to pause the video and then I'll resume it after I give you guys a chance to practice this. So here's the one that I want you to practice. We have log base 3 of the square root of x minus 4. Let's make that 12. Square roots of x minus 4 over the cube root of y squared, z minus 1 raised to the third. Oh, let's make it the fifth just so it's a different number. So all of this is the argument of the log, and I want you to expand this as much as possible. No, it's not. The question was, is z minus 1 to the fifth under the radical, and the answer is no. Okay, the answer to this, I'm going to write out the answer, and if you got it, great. If not, we need to talk about it. So this is going to be 1 plus, write 2 log base 3 of 2 plus 1/2 log base 3 of x minus 4 minus 2/3 log base 3 of y minus 5 log base 3 of z minus 1. Are there any terms up here you're curious about? This one, where did that come from? Good question. So what we want to do is we want to factor this thing. So this is going to be log base 3. That's your first step, is to rewrite the argument. Log base 3 of 12 you can write as 3 times 2 squared. X minus 4 to the 1/2 times y raised to the negative 2/3 times z minus 1 raised to the negative 5. The reason you want to factor this is we're simplifying. Anytime you have a log base 3 and 3 happens to be a factor of a number, you can pull that number out as a constant. This is going to be rewritten then when I expand it as a sum of logs. It's log base 3 of 3 plus log base 3 of 2 squared plus log base 3 of x minus 4 to the 1/2 plus log base 3 of y to the negative 2/3 plus log base 3 of z minus 1 to the negative 5th. Your next step then is to bring these exponents down. Well, there's no exponent here, but we learned this is the inverse property. I have a base and an exponent that are the same, so these are going to cancel each other out, leaving behind 1. That's just that very first property that we proved by rewriting it as an exponent. So this is going to then be plus 2 log base 3 of 2 plus 1/2 log base 3 of x minus 4 minus 2/3 log base 3 of y minus 5 log base 3 of z minus 1. If you have a base and you have a constant in your argument, and that base goes evenly into that constant, you can rewrite that using factors. That's why the 12 isn't there, because I rewrote 12 right here as 3 times 2 squared. So then I expanded it out, and there's my 3, and there's my 2 squared. We did the expanding thing, but I don't think I put an example in here where I ask you to contract. let me throw one in, because you've got to be able to go both ways with this, because those properties that we learned are equalities, meaning you can use them to expand, but you can also use them to contract. In calculus, we won't be contracting as much, but I want to know if you can do it. So I'm going to make up another problem. And the instructions here are going to be write the following as a single log. So we have the natural log of x minus 2 natural logs of y plus 3 natural log z minus 4 natural log 2 plus w. Rewrite this then as a single natural log. By the way, when you print out directions on MapQuest to go somewhere, do you print out the directions to go back home? No, you just follow them in reverse order. Remember these directions back here that I gave you for expanding? Let's now follow them in reverse order and see if we can do this. Power rule first. Okay, here's what this log will look like. It's going to be the natural log of xz cubed over y squared 2 plus w to the 4th. Did everybody get that? Alright, let's look at what we need to do then following these steps in reverse order. Your first step is to take any constants in front and move them up into the exponent. And guys, the sign goes with the numbers. That means the negatives need to go up. So what we're going to have here for our first step going in reverse order is the natural log of x plus the natural log of y to the negative 2 plus the natural log of z cubed plus the natural log of 2 plus w to the negative 4. The signs go with the number. Then we can rewrite this as a single log using the product rule in the reverse order. And that's going to give us x, y to the negative 2, z to the third, 2 plus w to the negative 4. And then we want to get rid of the negative exponents. And that's going to give us the natural log of anything with a positive exponent stays on top. Anything with a negative exponent gets made positive by moving it into the denominator. And that's what we got for our answer down here. Next problem, we want to approximate log base 3 of 12 and then round our answer to, how many decimal places did I say? 4? Most of us in the calculators that were required for the course do not have a log base 3 button, but we need a way around it. So here's what we're going to do. We are going to rewrite this as y equals log base 3 of 12, and we're going to solve this equation for y in such a way that we use a log button on our calculator. When we look at our calculator, we see 2 log buttons on here, don't we? We see the natural log and the common log. Remember, the common log is a log base 10, the natural log is a log base e. I do not have a log base 3 button, but this is still my instructions. When you're stuck and you don't know what else to do, rewrite the log as an exponent. And we do that using the definition of a log. Remember the definition of a log, and this needs to be committed to memory as soon as humanly possible. Y equals log base a of x if and only if a to the y equals x. Remember, it's an exponential, but we switch x and y. Rewrite this expression now as an equivalent exponent. What are we going to get? 3 to the y equals 12. Well, I have a little problem because I cannot rewrite 12 as a power of 3. If I could, I'd be there. I know what to do. And I can't. But I do have the power rule now. Remember that? And do you remember that whole conversation we had about logs are a mathematical operation like square root, addition, subtraction? It's just a new one that we're not that comfortable with. So what we're going to do is we're going to use that operation and we're going to take, in this case, the natural log of both sides of the equation. Remember, what you do to one side, you have to do to the other. So if I wanted to take a square root of one side, I'd have to take the square root of the other. If I wanted to multiply this side by 5, I'd have to multiply this side by 5. Well, what I want to do is introduce a log button that I have on my calculator And it can either use the natural log or the common log. It's just an operation, and I want to make sure it's 1 on my calculator. So this then, I'm going to leave the 3 to the y alone and the equals alone and the 12 alone. I'm just taking the natural log of each side. Now I want to use the power rule to get that variable out of the exponent. So we move it to the front, and that's going to give us y times the natural log of 3 equals the natural log of 12. Natural log of 3 is just a constant like 7 or the square root of 2. It's just a number. And it happens to be a number that you can use your calculator to get a decimal approximation for. So it's just a constant. When we have a variable times a constant, we're going to divide that constant off. So we divide both sides by the natural log of 3. What you do to one side, you have to do to the other. So we end up with then y equals the natural log of 12 divided by the natural log of 3. And do you remember me saying that this doesn't simplify using any rules? Oh, I have a question. Can I take 3 and divide it into 12 and just do the natural log of 4? No, you can't. Because that's in the argument. And in order to move things in an argument of a log, you can only use those special properties that we looked at. The product rule, the quotient rule, the power rule, the inverse properties. That argument of the log is just as sacred as the argument of a trig function, the angle of a trig function. You wouldn't go adding sine 1 plus sine 3 and get sine 4. You can't do that. You can't touch it unless you follow the rules. So at this point, we grab our calculator, and we're going to take the natural log of 12 and close the parenthesis after your log, divided by the natural log of 3. Now we've got our decimal approximation. To 4 places, it would be 2.2619. So this is approximately 2.2619. Would it have mattered if I'd have used the common log instead of the natural log? Just to prove the point, I'm going to hit second enter, and I'm going to change my natural logs to common logs. So instead of an ln, I've got a log. It's the same thing. That's because when we did this over here, taking the natural log of both sides, we did the same thing to both sides. So if I would have done a common log instead of a natural log, it'd be okay. What you can't do is mix common logs with natural logs. They both have to be the same. And what we see here then can be generalized into a change of base formula. The change of base formula says log base a of x is equal to the natural log of x divided by the natural log of a, or the common log of x divided by the common log of a. Well, they use different letters, but hey, there you go. That's why I just generalized this. See, the 12 was higher than the 3. The 12 is higher than the 3. And that's how I remembered these. I knew that if I had a log base something other than 10 or e, I could use the change of base formula, and I remembered that it would be a log over a log, but I'd get screwed up as to which one went on top and which one went on bottom. Then one day, I noticed this one's lower. It's a subscript. Guess where it ends up? Lower. And after that, I never forgot which one went on top and which one went on bottom. So remembering it wasn't a big deal. Let's use the change of base formula now in order to get these values. On A, we want to find log base 5 of 89. You can either use the natural log or the common log, whichever your favorite log is. ln is easier for me to write, so that's the one I'm doing. This will be the natural log of what over the natural log of what? 89 over 5. So we go to the calculator, and we want this rounded to 4 places, so it's going to be the natural log of 89 divided by the natural log of 5. And we get 2.7889. On B, we have log base square root of 2 of square root of 5. This is going to be the natural log of the square root of over the natural log of the square root of 2. I don't know why I put that in parentheses. You didn't have to. You do have to be careful about how you type this in, though. So there's our natural log. And then when we hit square root, we hit second x squared, because it's an inverse function, 5. Close the parentheses for the radical, then close them again for the log, and divide it by natural log of the square root of 2. So this is 2.3219. If you have the newer operating system, it'll automatically put it under the radical and not worry about the parentheses. Rounded to 4 places because that's what we were told to do in the instructions. And then here's a summary of the properties of logs. This is something that would be nice to print out and have in front of you as you're doing your homework. No, you don't get this on this test. Know these rules. And you should, between now and next Thursday, do so much homework that you can't help but memorize these rules.